All right, well, I'll start this off very quickly. So good morning, everyone. We're very proud to welcome you to this first collaborative young member webinar between RILEM and ACI. It is my pleasure to introduce you to a couple of people who are going to lead this thing in good, you're going to be in good hands with those people. So I got Olga Kakashi over here, who is our North American representative on the RILEM Youth Council. We got Jose Gonzalez Aviña here, who is the Latin American representative on the RILEM Youth Council. And then we get Alvaro Ruiz Esperanza, who is the current chair of S806 from ACI, and that committee focuses on young members. I'll give them the floor. I'll shut up here. I'll give them the floor to introduce RILEM, to introduce ACI, and then to actually co-moderate this entire webinar over here. So thank you for joining us, and I hope you enjoyed this webinar.
Hi, Dimitri. Thank you so much for the kind introduction. Again, it's a great pleasure for all of us, especially Jose and Alvaro, to be the moderator, together with Dimitri, to be the moderators for this first edition of the joint webinar between RILEM and ICA. Before starting, I would like to take the opportunity to introduce RILEM Youth Council and provide some background information about our work and goal. I'm going to share my screen with a quick presentation. So RILEM Youth Council was formed in 2020. It has 10 members, each representing a different region of the world, plus Joanita, who serves as the chairperson. The council was created with the aim of connecting young researchers worldwide, fostering a community of dynamic individuals, and promoting active participation in RILEM activities and the broader research community. In 2021, we focused on attracting young members via emailing campaigns and creating content on Instagram. In 2022, we created the peer-to-peer webinar series to strengthen participation and connections within the RILEM youth community. One of the primary objectives of the RILEM Youth Council is to identify young researchers who are experts in various domains of construction materials and provide them with a platform to disseminate their knowledge to other young researchers like you. Also, the aim is to showcase relevant examples of quality research within the young community of RILEM. We have planned to schedule this webinar every 2 months, and it will be region-specific. To conclude, today, the region under focus is North America, and in July and May, we had the webinars in other parts of the world, such as the Pacific and the South Asian region. And please feel free to reach out to the RILEM Youth Council representative of your region or contact RILEM secretary if you would like to be part of the webinar series or if you would like to join RILEM. And now, well, thank you so much for again for being with us today. I want to leave the floor to Alvaro.
Sure. Thank you, Olga, and good morning, everyone. Let me share my screen as I talk a little bit about ACI, specifically S806, which is the subcommittee. Let me see if I can start it. Okay. So S806, which is the Young Member Activity Committee, it's a subcommittee from SIPAC. SIPAC is the Student and Young Professional Activity Committee within ACI. So we are very happy to partner with RILEM to host this webinar. So this is us. We have 3 leadership positions. Myself as a chair, David Orense, who is also pretty involved in RILEM as a co-chair, and then we have Maya as secretary. And of course, we do have a lot of members that contribute to the subcommittee and make it great. So what do we do? So our mission is to promote the membership of younger members in ACI and to encourage a little bit the involvement within the ACI as an organization and at conventions, of course. So for that, here are 4 different programs that we have in place. We do other things too, but these are the main ones. First one, so we provide free convention registration to 2 to 4 young members per year. We know that a lot of times it gets expensive to go to these conventions, so at least we get some of them this complimentary registration. We also partner with the Emerging Leaders Conference, which is it's a program where they foster the management of young professional, young leaders. So we bring two members from the ACI to this conference. In addition to that, we have what I wish I knew session. So this is a session for professional development. We do it once a year in the ACI convention. And on this one, we try to talk about different current research and other technical topics for young members again. And last but not least, we have a podcast. In this podcast, we talk about more real life topics such as work-life balance, and again, this is tailored for young members. So, without further ado, I'll stop here since we have two great rock stars today that we should leave time for them. So, Olga, do you want me to start introducing them?
Absolutely, thank you.
Okay. So I have the pleasure today to introduce a colleague of mine from the ACI, Robert Thomas, Dr. Robert Thomas, I would say. So Robert is an assistant professor of civil engineering at Clarkson University in Potsdam. His research mission is to engineer concrete solutions for the next generation of civil infrastructure. His core expertise is in alternative cements, supplementary cementitious materials, concrete durability, and sustainability. More recently, his interests have included infrastructure materials for extraterrestrial construction. He has authored more than 50 journal articles and conference papers related to concrete materials and structures. Thomas is active in the American Concrete Institute, where he chairs Committee 242 on alternative cements and is a voting member of Committee 123 on research and current developments and Committee 565 on lunar concrete. Today, Robert will be presenting his work titled Space Concrete, the Final Frontier. Okay, and I think I missed to introduce the entire webinar itself, which is, we mentioned it at the beginning, but the session is titled The Cementitious Materials for Advanced Construction. So Robert is one of the presenters of this entire webinar. So just to talk a little bit about the logistics. So if you have any questions during the presentation, please feel free to type them into the question box, and then we'll go through those questions and tackle them at the end of the session. So we have two videos that are pre-recorded to avoid any technical trouble that sometimes that happens with this type of webinars. So the speakers but afterwards we'll have the speakers here, so you can read, they can read the questions in real time, and they can reply in the Q&A box. So it's going to be a mixed. So yeah, without further ado, Olga, do you want to take it from here?
Yes, I'm gonna play Thomas' video.
Perfect.
Hi, my name is Robert Thomas, and I'm an assistant professor of civil engineering at Clarkson University in northern New York State. My mission is to engineer concrete solutions for the next generation of civil infrastructure. And I'm here today virtually to talk to you a little bit about lunar concrete. My title, Space Concrete, the Final Frontier, is a bit of a joke. This is a quote from an old American TV series from the 1960s called Star Trek. It called out to me as I was thinking about this presentation, and what struck me was that 60 years later, space is still the final frontier. Our quest to learn more about the universe around us is one of the most quintessential engineering challenges of the modern day, and nowhere is that truer than in the civil engineering and construction sectors. For millennia, we have worked to optimize the design and construction of civil infrastructure, the systems and structures that keep society comfortable. But for millennia, we've been tethered to this planet that we call home. And all of that is about to change. Before we talk about that, let's take a short trip through the history of concrete. We hear a lot today about unlocking the secrets to Roman concrete. A lot of folks say that the Romans invented concrete, but that's not quite true. In fact, we have evidence as far back as 8,000 years ago of the Nabateans building masonry cisterns with hydraulic lime mortars. And there's evidence of Egyptian societies making masonry mortars 5,000 years ago. The Romans built the Pantheon roughly 2,000 years ago. And it was almost exactly 200 years ago that an English bricklayer named Joseph Aspdin patented Portland cement, which is still the basis of nearly all the concrete we make today. Reinforced concrete didn't emerge until 1867 when a French gardener named Joseph Monnier used steel rods to keep his concrete garden beds from cracking. 20 years ago, and less than 150 years after the invention of reinforced concrete, construction began on the Burj Khalifa, which still stands as not only the tallest concrete structure, but the tallest man-made structure of any kind. And just a few years ago, cements were hydrated aboard the International Space Station for the first time ever. Let's talk about another critical date, December 7th, 1972. That was the last time a human being set foot on our nearest celestial neighbor, the moon. Apollo 17 was the 11th and final mission of NASA's Apollo program, which visited Earth's moon 6 times between 1969 and 1972. Each mission provided invaluable data about the geography of the moon, the composition of its soil, the conditions of its atmosphere, and more. But by 1970, the cost of the Apollo program had become astronomical, the public had lost interest, and NASA scrapped its plans for further trips to the moon. Artemis, the twin sister of Apollo, is a fitting name for NASA's mission to bring humankind back to Earth's moon. Initiated in 2020, Artemis will bring the first woman and the first person of color to the moon. It will establish the first long-term human presence on the lunar surface, and it'll use the moon as a stepping stone to reach our next nearest celestial neighbor, Mars. As part of the Artemis mission, NASA's Moon to Mars Planetary Autonomous Construction Technology, or MPACT program, is developing technologies to support construction of key infrastructure on the moon. Repeated missions to the moon will require landing pads to prevent dust plumes, which can take hours to settle in the moon's low atmosphere. Extended human presence on the moon will require pressurized habitats and life support systems to protect occupants from the harsh conditions on the lunar surface. Broad exploration of the lunar surface will require roads, shelters, berms, and other civil infrastructure, and NASA has ambitiously targeted the late 2020s for the first demonstration-scale lunar projects and the early 2030s for construction of the first landing pads. The Microgravity Investigation of Cement Solidification, or MIX project, was a collaboration between NASA and Penn State that was really the first step in the development of lunar concrete technology. Its purpose was to understand how the reduced gravity of the moon and Mars would influence how cements solidify. Would the pore structure be different? Would different hydration products form? Would they have different structural and mineralogical properties? Dr. Redwinska and her team at Penn State sent cement samples to the International Space Station, where they were hydrated at microgravity, which is as close to 0 G as we could get, as well as at equivalent gravities to the moon and Mars. They also prepared companion samples in the terrestrial laboratory at 1 G, so we could compare the properties of space-hydrated and Earth-hydrated cements. They were kind enough to share some of those samples with us so we could study their microstructures and properties. And here you see 3 Portland cement samples with lunar simulant aggregates that were hydrated at microgravity, lunar gravity, and Earth gravity. One of the most obvious changes we see is the appearance of coarse air voids in the space-hydrated samples. It turns out that gravity is extremely helpful in consolidating the fresh concrete. We need phenomena like buoyancy to help air bubbles settle out of the fresh concrete, and these effects are diminished at lower gravity. Of course, we know that air voids represent stress concentrators inside the microstructure, and we know that these macroscopic air voids greatly weaken the strength of the material. But they also make it more permeable, which presents another problem for structures that need to be pressurized. And this is yet another challenge that we'll need to work to address. We wanted to learn about the strength of the material, but it's very expensive to send samples to the space station, so the samples we send are far too small to perform any mechanical tests. So we do something called nanoindentation, which is when we take a microscopic probe and indent the surface along a grid pattern to see how hard and stiff the material is at that location. This helps us understand the strength of the particles within the microstructure, which we can then feed into a numerical model that might help predict the structural scale properties. You can see here that the aggregate particles are quite hard, while the hydrated cement paste that binds them together is quite a bit softer. Interestingly, we find that the micromechanical properties don't change very much at reduced gravity, which tells us that the dominating effect of microgravity is actually on the consolidation of the fresh concrete and the resulting impacts on the air void structure. This is important because once we understand the mechanism at play, we can theoretically design solutions to overcome that effect. As I said, though, the mixed study focused on Portland cement. And while it helped form a basic understanding of how cementitious materials might behave on the moon or Mars, Portland cement is really not a viable option for lunar construction, and the primary reason is cost. Let's do a quick thought exercise. It costs about 2 million euros to transport 1 kilogram of material from the Earth to the moon. And normal weight concrete weighs about 2,400 kilos per cubic meter. So let's say we want to construct a landing pad. Maybe it's 20 by 20 meters and 300 millimeters thick. That seems like a reasonable landing pad to land a lunar lander. This equates to about 120 cubic meters of concrete and a projected cost of 240 million euros just for transportation of the raw materials. Maybe we want to construct a 20-meter dome, some type of human habitat. Maybe it has 100 millimeter thick walls and sits on a 200 millimeter thick circular foundation. This is a pretty small habitat actually, and could potentially house maybe a small handful of people. That equates to 200 cubic meters of concrete for a projected cost of 400 million euros just for transportation of raw materials. This is clearly not sustainable, so we need to find a better solution. That better solution is in situ resource utilization, or ISRU. According to NASA, ISRU harnesses planetary resources at mission destinations to enhance the capabilities of human exploration. In other words, ISRU is using what's already there. Obviously, if we're to achieve a sustained human presence on the moon, we need to learn to harness the resources it offers. In terms of construction materials, the moon has rich resources in the form of lunar regolith. That's just a scientific term for the lunar soil. And on the right, you see an image of Buzz Aldrin's footprint in the lunar regolith from the 1969 landing. There's also some water on the moon, but it's relatively scarce, somewhat difficult to extract, and it'll need to be conserved. Fortunately, over the last several hundred years, concrete researchers have developed a pretty robust toolbox of technologies that can be used to make concrete. One of those technologies is geopolymers, or alkali-activated concrete. Geopolymers are cement-like binders that are made by combining an aluminosilicate material with an alkaline activator. On Earth, we make geopolymers with fly ash or slag cement, but this technology works with just about any aluminosilicate material, of which the lunar regolith happens to be one. Interestingly, the lunar surface also contains some extractable alkalis, so the activators could potentially be produced using the principles of ISRU. And finally, geopolymers do require water for mixing, for workability and consolidation, But the geopolymerization reaction is actually water neutral, so that water could potentially be recaptured. So lunar regolith-based geopolymers seem like a pretty promising solution. But only a few hundred kilograms of actual lunar regolith have been collected from the 6 Apollo landings, and unfortunately, NASA is not about to give that away to a bunch of concrete researchers. Fortunately, however, various parties have produced what we call lunar simulants. These are carefully selected and graded mixtures of Earth minerals like volcanic glass and feldspar that can mimic the actual lunar regolith. Some of these are very basic simulants that model the geotechnical properties of the regolith, and some are more specialized simulants that mimic the chemistry or mineralogy quite closely. We've used a variety of simulants, including the one I show here, which is JSC-1A, which stands for Johnson Space Center 1A. And even though this is made from terrestrial materials, the supplies are still quite limited. And with JSC-1A, actually only 40 tons of the material were ever produced, and it's currently out of production. So these samples are still quite precious. Our colleagues at Penn State used JSC-1A and a variety of other simulants and a series of alkali activators to produce lunar simulant-based geopolymers. And again, they graciously shared some of the samples with us at Clarkson. One of the most interesting things we observed were the microstructures of the geopolymer samples. And here you can see an example of that. You can see a few large air voids in the image on the left, where the largest air voids are about 100 microns or 0.1 millimeters wide. But in the close-up image on the right, where the simulant particle in the middle is only about 25 microns wide, we can see that the simulant particles are joined together by a dense, continuous, and well-refined cementitious binder. Even without performing macro-scale testing, this tells us that the degree of reactivity is very high, which suggests that the material was going to be both strong and durable. Not all the geopolymers work well. Here's another sample with a different simulant and a different alkaline activator. And even in the very zoomed out view of the microstructure on the left, you can see that it's much coarser and more discontinuous than the previous one. In the close-up view on the right, you can see how the simulant particles are no longer well connected. The paste matrix between them is sparse and poorly refined, and this suggests to us that this combination of activator and simulant would perform poorly as a geopolymer. Practically, that means either the activator is a poor choice and perhaps a stronger concentration would lead to better polymerization, or the simulant might not be very reactive, indicating that lunar soils with this kind of composition are not suitable precursors for lunar concrete. Based on that, we could guess which regions of the moon could be mined for geopolymer precursors. Here's a third set of microstructures. This is yet another simulant and activator combination, and this microstructure is really somewhere in between the previous two. We've got a lot of coarse air voids in the image on the left, and in the image on the right, the paste matrix is fairly well developed, but still a bit coarser than the best performing mixtures. So again, maybe we need to increase the activator concentration to achieve better reactivity. But really what I want to focus on in this slide are all these air voids in the image on the left. We saw similar air voids in the mixed samples earlier, and we said the air voids would form stress concentrators and weaken the strength of the material. These air voids can happen due to reduced gravity like they did in the mixed samples, but they can also happen due to a variety of other effects. Reduced gravity is not the only challenge posed by the lunar environment. We also see dramatic temperature fluctuations and the lack of an atmosphere. On Earth, atmospheric pressure helps with the closing of air voids in the fresh concrete. The image on the left is lunar concrete formed at 1 atmosphere of pressure, and the microstructure is dense and well consolidated, and there are no macroscopic air voids to speak of. The image on the right is lunar concrete formed at reduced atmospheric pressure. The lower pressure means the air bubbles don't collapse. Instead, they remain in the microstructure as it hardens, leaving the very large air voids you see here. These air voids dramatically weaken the strength of the material, which is yet another challenge we need to overcome. By the way, NASA and partners have investigated using pressurized tents to provide some artificial atmosphere during construction, but this will come nowhere near the atmospheric pressure we experience on Earth. The weathering conditions on the moon are another critical challenge. Without an ozone layer, lunar structures experience much stronger solar radiation than Earth structures. They'll also experience significant temperature fluctuations and constant abrasion by lunar dust and microasteroids. We need to know that they'll hold up to these aggressive conditions. So NASA and our partners at Penn State sent some lunar concrete samples to the space station and put them outside in a special platform where they were exposed to the low Earth orbit for about 6 months. They flew the samples back to Earth and we cut them perpendicular to the exposed surface to look at their microstructures. Here you see 2 of those samples, where this black region at the top represents the exposed surface. The top sample experienced significant surface cracking, probably due to thermal cycling. The bottom sample experienced a lot less cracking. The difference here is that the bottom sample was fiber reinforced and the top sample was not. You can see some of the fibers right here. So we know from this that fiber reinforcement is probably going to be a critical part of lunar concrete in order to produce durable lunar structures. So clearly we have a lot of work going on and we're trying our very best to develop lunar concrete technology and solve the various problems that appear along the way. But at this point, I think it's very important to acknowledge that our part of this work is small. There are so many other material technologies being developed that are just as promising, if not more promising, than lunar geopolymers. There are calcium sulfoaluminate precursors on the moon that could be used to make ettringite-based cements. This image shows the needle-like ettringite crystals that are the basis of these high early strength binder systems. There's also microwave sintering of the lunar regolith, where the regolith itself is melted and fused together to form a solid matrix. This is probably the most mature technology, and a great deal of thought has been put into how it can be used to make landing pads on the lunar surface. Here's one iteration where a lunar rover could theoretically be used to autonomously grade, compact, and sinter the regolith, forming a landing pad. There are also a series of other technologies that are quite promising. But there's an even bigger picture beyond that. We've only talked about the construction materials part of developing lunar infrastructure. If we zoom out even further, we realize that the materials side of this challenge is still only a very small part of the mission. There are so many other barriers to extraterrestrial construction that need to be removed or overcome. We need to provide power and life support systems. We need to handle raw materials extraction and manufacturing processes. We need on-site testing and quality assurance. So while it's appropriate for us to have some pride in our work and the advancements we're making, it's equally important to have some humility and recognize that we're part of a tremendous multidisciplinary team working together to solve an enormous challenge. With that, I would like to thank my students, collaborators, and sponsors, in particular, Soleiman Dawood and Peter Collins, who generated most of the data and samples that I discussed today. Dr. Redlinska at Penn State, who is certainly the world's foremost expert on lunar concrete. And finally, our sponsors at NASA, who've provided the financial support for this work. Thank you all very much.
Perfect. So thank you very much, Robert, and for presenting your work. And for those who didn't, please feel free to put your questions in the Q&A box. And at the end of also Jean-Jacques' presentation, we're gonna start to listen to the response from our expert. So I think we can now move to the second speaker, which is Jean-Jacques Gupta, who is a PhD candidate in the Civil and Environmental Engineering Department at Princeton University. His research focus is to develop tough cement-based materials using bio-inspired architectures. His research areas include architected materials fracture mechanics, and additive manufacturing. He has authored more than 14 journal articles and conference papers on cement-based material. He's also an associate member of ACI Committee 564, which focuses on 3D printing with cementitious material. Today, his presentation will focus on tough cortical bone-inspired tubular architecture cement-based materials. I'm gonna now play his video.
Hello, everyone.
One second.
Hello, everyone. My name is Shashank, and I'm a PhD candidate in Reza Moini's lab at Princeton University. Firstly, I would like to thank RILEM and RILEM Youth Council to provide me an opportunity to present my work here. Today in this webinar, I will be talking on tough cortical bone-inspired tubular architecture cement-based material. Let's start with a bit of a background. Ordinary concrete has limited ways to dissipate energy in the process of fracture. This is due to limited toughening mechanisms such as crack shielding, due to micro cracks, crack deflection, crack aggregate bridging, crack closure induced by surface roughness. These limited toughening mechanisms leads to relatively small length of fracture process zone. Therefore, not to our surprise, concrete material are either brittle or quasi-brittle under tension. Now, question I would like to ask whether we can develop tough concrete without changing composition as a new way to enhance the inherent resistance of cement-based material to fracture. In other words, can we engineer cementitious material to have fracture resistance? What can help us to develop these material is the flexibility provided by the fabrication processes and the opportunities provided by the design of the material structure. Now, the material structure can be either microstructure or mesoarchitecture. The design of material architecture can be used to tune the fundamental properties of the material to obtain the desirable performance, in contrast to the monolithic brittle solid. This further helps us to overcome the mutual exclusivity between strength, toughness, and stiffness. Today, I will be only focusing on the strength and the toughness aspect of the material. When it comes to design, can we learn from nature? Let's look at the microstructure of the bone. So the human femur bone is composed of outer tough cortical bone and the inner porous spongy bone. The cortical bone has 2-order higher fracture toughness than its constituent material, hydroxyapatite crystal and collagen. This increase in fracture toughness can be attributed to the presence of tube-like osteons embedded in the cortical bone. These osteons are weakly bonded to the organic matrix through these cement line. The cement line has nothing to do with the cement, just to avoid any confusion. The cement lines are 10 times weaker than the osteons. So when the crack start to propagate in the cortical bone, these weaker cement lines provide microstructurally preferred path for crack to propagate, hence triggering toughening mechanisms like crack deflection through cement line interaction in cortical bone. Taking the inspiration from the cortical bone, we want to engineer these toughening mechanisms in the brittle cementitious material using tubular architecture. Furthermore, by tubular architecture, we mean the tubeless cement line around the osteon, not osteons themselves. So let's see how do we fabricate them. Firstly, you can directly 3D print them. To do so, we have developed parametric contours like graded sinusoidal and elliptical to print tubular architected material by defining the input geometrical parameters. These contours can then be converted to G code. In order to execute the whole process, we have developed in-house algorithms in Grasshopper and Rhino. Furthermore, there are several approaches to control the tool path. However, I won't get into the details for the sake of time. Another method that we can use is a hybrid process in which we 3D print a PVA mold, then cast urethane rubber into it and demold the PVA to make this urethane rubber mold. Then we use this urethane rubber mold to cast the cement paste. This method enables direct formation of tubular system and cementitious material. And this is also the approach that we have used for what I will be presenting today. Let me expand a bit on design parameters. So we have fabricated tubular architected material with porosity varying from 20 to 50%, and aspect ratio varying from 1 to 3, where 1 denotes the case of circle and any other value denotes the case of elliptical design. These parameters corroborate well with the volume percentage and the aspect ratio of the osteons in the cortical bone. Furthermore, I will be only highlighting the case of circular design with 40% porosity and the elliptical design with 40% porosity and aspect ratio to end this presentation for the sake of the brevity. The mechanical response was characterized by modulus of rupture and fracture toughness. The modulus of rupture was characterized using the ASTM C78, and for fracture response, the ASTM E1820 was used. In fracture, the compliance method was being used for crack extension, and combined J-elastic and J-plastic terms have been used to calculate the fracture toughness as the crack propagate. We have also plotted R curve to show the resistance to crack growth in terms of the fracture toughness. So, what did we find? Let me show the highlights of some of the results for some of these designs. So the load displacement response of notch specimen demonstrate that the architected tubular material that is being represented by blue color and the red color shows a unique non-brittle fracture behavior compared to the brittle solid counterwork showed by the gray line. The architected tubular design demonstrate multiple hardening and softening behavior, which is evident from the multiple crack initiations. The R curve shows that the toughness of the tubular architected material increased with the extension of the crack in a stepwise manner. This increase is directly correlated with the load displacement plot, where the softening corresponds to the crack extension and the hardening corresponds to the steep increase in the R curve. We hypothesize that the stepwise cracking through the tubes is the toughening mechanism which lead to an increase in toughness. To better understand the crack propagation in the tubular architected material, we carried out digital image correlation on the fracture rest. You can see that following the crack initiation from the notch, the softening correspond to the crack extension in the both circular and elliptical design was observed. On the other hand, each hardening corresponded to the initiation of the crack from the tube. These experimental findings from DIC validates the hypothesis of the stepwise cracking. More importantly, when we look at the specific crack initiation and crack propagation fracture toughness, the specific crack initiation fracture toughness remains unchanged. This is the good news because that means we can increase the porosity in the material while maintaining toughness. When we look at crack propagation fracture toughness, an increase of 3 to 5.6 times from solid material to tubular architected material was observed. And all this happened while the specific strength remained constant. So the gain goodness. For a better understanding of the toughening mechanism, we looked into the theoretical analysis of stress and density factor and stresses at failure of crack in the tubular architected material. Stress intensity factor is used to predict the stress state near the tip of the crack or notch caused by the far field stressor, that is sigma x infinity. The stress intensity factor in the presence of a tube can be defined in terms of the stresses on the crack in the uncracked body due to tubular elliptical void, as shown by this blue sigma x. Now, the sigma x can be obtained using the Mushkeli's-Rayleigh equation. We are also defining the stress intensity factor ratio, which is simply the ratio of the stress intensity factor of material in the presence of tube over that of solid. The SIF ratio, defined as F, will aid to easily look at the effect of the presence of tube relative to its absence. That is the case of the solid material. Now here I'm showing the plot of stress intensity factor and far field stress in the solid, and the presence of and in the presence of the tubular void of circular 40% and elliptical 40% with the aspect ratio of 2.5. So in a brittle material such as cement base, crack initiate when the stress intensity factor becomes equal to critical stress intensity factor, according to the Griffiths energy balance approach. Consequently, the intersection of stress intensity factor and far field stress plot with the critical stress intensity factor yields the far field stress at which the crack initiation takes place, as shown by sigma x infinity solid. We can see that the stress at failure in the tubular architected materials is smaller than the stress at failure of the solid. Even the previously presented definition of stress intensity factor ratio, we can define the stress at failure in tubular system as the stress at failure of the solid counterpart over the SIF ratio. In the same way, the loaded failure in the tubular system can be also defined in terms of the SIF ratio. Using this SIF ratio, we can also look at the effect of the tube size and shape. Based on our discussion in the last slides, we have calculated the stress intensity factor ratio for different porosity and aspect ratio of tubes. For solid system, in the absence of the tube, the SIF ratio is 1. That makes sense. We can say that the presence of the tube position in front of the crack increases the stress intensity factor at the tip of the crack. The SIF ratio increases with the increases in porosity, and it decreases with the increase in aspect ratio, which is an interesting find. Using the relationship between the SIF ratio and the load at failure, we have also plotted the theoretical load at failure for different porosity and aspect ratio. We can see that the theoretical load at failure decreases with an increase in porosity and increases with an increasing aspect ratio. The theoretical trends for the single tube also match the experimental trends of the load at failure for a fully tubular system. The results regarding the load at failure indicate that the tubular system with higher porosity and lower aspect ratio exhibit a lower load at failure, which negatively affects the fracture toughness of the cement-based material. However, the same characteristic of higher porosity and lower aspect ratio in the tubular architected material facilitate the stepwise cracking, which in turn increases the material's fracture tolerance. Hence, we can say that load at failure and stepwise cracking have competing effects on the failure tolerance. If you look at the broader range of the tube size and shape, the competing effect of loaded failure and the stepwise cracking gave rise to optimal fracture toughness in certain cases. For instance, among the circular cases, the porosity of 40% exhibits the best fracture toughness as shown by the blue dots. On the other hand, among the elliptical cases, the porosity of 40% and aspect ratio of 2.5 exhibits the highest fracture toughness as indicated by this red dot as well. The theoretical analysis that I showed before for the stress intensity factor was conducted for a single tube. The superposition of multiple tubes and the positive and negative effects of their location on the stress intensity factor can be considered to better capture the experimental analysis. It is also interesting to note that the SIF ratio of the crack tip increases or decreases depending on the position of the tube from the crack tip. The theoretical determination of the stress intensity factor can be extended for better comparison of experiments and analytical model, considering both the superposition of the effects of multiple tubes at various locations ahead of the crack tip, as well as the bending stress state. To put it all together, let's see where is all the sample lengths on the Ashby plot. So all the tubular architected material exhibited higher specific fracture toughness than the reference cement base. Tubular architected material shows fracture toughness in the range of mortar to the upper boundary of the granite. Zooming into the plot, we can see that circular 40% shows specific fracture toughness close to the upper boundary of the fiber reinforced cement base, whereas elliptical 40% with the aspect ratio of 2.5 showed the highest specific fracture toughness among the tubular architected material, and it is even higher than the fiber reinforced cement. In conclusion, we showed that hybrid or additive manufacturing can be used in a variety of ways to architect material. However, further work on scaling up is necessary. We also learned that toughening mechanism inspired from bone can enhance the fracture toughness of brittle cementitious material up to 5.6 times. The stepwise toughening mechanism can be further engineered by the competition between the tube size and shape on the failure stress intensity factor and loaded failure. And finally, considering our first question, can we make a brittle material tough and non-brittle without changing composition? Yes. By engineering the architecture, we can achieve toughness strength trade-off without changing the composition. Digital workflow for additive fabrication can help make realization of these materials more viable and accessible. Moving ahead, I would like to thank my advisor and director of the AM2 lab, Professor Reza Moini, for his support over the last few years. I'm also grateful to fellow graduate students, postdocs, and undergrad in our team for their innovative contribution through several discussions. I'm also grateful to NSF Career and NSF ACI for the partial funding of this project. Thank you for your attention. I'll be happy to take any questions now. Please also feel free to contact me if you have any more questions or suggestions through the email. Thank you.
Well, thank you so much, Shashak, for the presentation. And I would like to again suggest to the audience to post their last questions for both Robert and Shashank. Albert, I think we can start with a question for Robert.
Yeah. So I saw there's a question that has already been answered, Robert. I don't know if you want to elaborate a little bit more.
Yeah, sure.
I can do that. Yeah, so someone asked if anyone had looked at the sintering kinetics of the lunar simulants or of the formation of CSA cements in any rigorous way. And CSA cements have been around for a really long time. There's a huge body of research on those. They were invented in the 1960s, so there's a lot of information on that. I'm not exactly sure about the kinetics of sintering, but I did pop a link in the text answer here that has a really good review paper that was recently published if you're looking for more information on the sintering of lunar simulants. I think that's a great place to start.
Perfect. Thanks, Robert. I see that I see another question. Ahmad Hassan is asking you, Robert, about the type of fibers that were used and if there is any consideration for fillers at certain gradation range to fill the voids.
Yeah, that's a really good question. So they were just regular plain steel fibers, what we would use for something like UHPC. In terms of the fillers, what we have to remember is everything or as much of what we are making has to come from the lunar surface. And so really the discussion around the use of fillers and gradation is how can we, perhaps do some fractionation of the lunar regolith to just get the particle sizes we need. We do see that it's mainly the smaller particles that are polymerizing. And so if we can figure out a way to mechanically separate the particles on the lunar surface, that would be a tremendous benefit. In terms of bringing fillers, that's not going to be an option. You see a lot of with nanosilica or other nanoparticles used as fillers on Earth. We just can't afford to bring them there. But there has been a lot of discussion about fractionating and regrading the lunar regolith to make it more reactive and to get a better packing density.
Thank you, Robert. I have another question here by Renato Sahade. He's asking about the cement hydration products that you see during the process of hydration.
When we send Portland cement to the space station hydrated in microgravity, we see the exact same products we see on Earth. We get high and low density CSH, and we get calcium hydroxide. And they're mechanically similar to the phases we produce when we hydrate cements on Earth. When we're doing the geopolymerization of the regolith simulants, what we get is the formation of what we tend to call just a geopolymer gel. It's a sodium aluminosilicate hydrate, which is identical mechanically and physically to the sodium aluminosilicate hydrates that we form in terrestrial geopolymers. So the only difference is that fly ash tends to be like 90% amorphous, and so it reacts almost completely. The regolith is like 25 or 30% amorphous, and so the big difference we see is that there's just not as much of that geopolymer, that sodium aluminosilicate hydrate gel, as we would see in a fly ash based geopolymer. But the product we do form is essentially the same in morphology and mechanical properties as what we would with a fly ash geopolymer.
Thanks, Robert. Appreciate
Thank
it.
you.
Olga, do you want me to take another question for Robert, or do you want to switch gears, as I know that we have 5 minutes?
Yeah, maybe we can continue with the question for Shashank, and we can come back. So I think we have one question for Shashank. In terms of dynamic loading and impact loading, did the research extrapolate?
So what we have done is for a fractured sample that has with a sample with a stress concentration in terms of a notch for the fracture to understand the fracture response of material. So if we have a notch sample and we change this loading condition to dynamic or impact loading, we might be able to see these stepwise cracking toughening mechanism depending on the frequency and the amplitude of the dynamic loading in term with respect to the failure strength of the material. However, if we have a solid composite and we do not have any notch or the crack initiation, then it might be very hard to comment about it in terms of dynamic loading or impact loading.
Dimitri, I don't know if you want to add something. I saw. Okay. Thank you so much. I think the rest of the
Maybe
here
the
we
last,
have-
maybe
yes,
the last one.
exactly. We have a last one for Shashank. To the printed materials that layered. Can you elaborate on how bio-inspired designs principles can be translated to improve mechanics in layered, for example, 3D printed brittle and quasi-brittle materials?
So in 3D printed material, these layers act as defects, like because we have seen that these three in the interfacial regions of the 3D printed material, there's higher porosity relative to the filament area. So hence these material are heterogeneous. So these heterogeneities can be engineered in such a way that we can take benefit of several toughening mechanisms. For example, I'm showing here tubular, but there are other architectures like Bulligand architecture that have these these interfacial regions can be interfacial region can be changed relative to the one layer to the other layer, so that we can engineer toughening mechanism like crack deflection and crack twisting. There's other things that we can do, like introducing another material in these interfacial regions to also introduce other toughening mechanisms like crack deflection and stepwise cracking in these 3D printed material.
Well, thank you very much. I don't see for the question. Maybe we can have maybe I think we should. I don't know if you have the time for another question, since we have only 2 minutes. However, I really wanted to thank both speakers because I really loved the two completely different frameworks to begin with, by using, let's say a common material, which is in this case cement, concrete. And on one hand, we had a really microscopic approach trying to simulate bio-inspired structure, and on the other hand, a framework with respect to new gravity and different material resources. So I think this was very powerful and interesting. And again, I think we can go to the end of this webinar. I hope that we all learned something new. The presentations were very, very interesting. Thank you again, Robert and Shashank, for being with us. And please, regarding the videos, you're gonna see the recording of this webinar, and also the 2 videos in our channels in the RILEM pages, and also in the ACI. We will keep you updated for further and future events. And Alvaro and Dimitri, do you want to add anything?
I think I just want to extend the thanks on behalf of ACI. I think it was a great event. Thanks Olga and RILEM team for helping us put together. And of course, our presenters who were the rock stars of today. So thanks everyone, all the attendees. And I don't know, Dimitri, do you want to add something else on the ACI?
I think just in the name of both the organizations, ACI and RILEM, I want to thank you for your attendance and participating actively in this webinar. You've been a great audience. Thank you.
Before leaving, I'm going to take a screenshot for all of us, so please smile. Okay, wonderful. And see you at the next event.
Sounds good.
Thank you so much, everyone.
Thanks, everyone.
Thank you, everyone. Thank you, everyone. Bye. Have a good day, afternoon, morning, whatever.